Welcome back to ECE 320A. In this very short video, what I want to do is just illustrate or derive the Laplace transform of the impulse, and it really is quite straightforward once we recall what the impulse function does when it's inside the argument of an integral. If we remember what's happening with an impulse, that's just infinitely tall, infinitesimally narrow function. It's not really a function, but we call it a function. This impulse expression, that's the only time that it's defined is in this infinitesimally narrow time interval across, in this case, when the argument is 0, is at t equal to 0. The only thing that it can possibly do then when you multiply it by a waveform f of t is do something with that function at the time that the impulse occurs. In this case, the impulse occurs at time t equals 0. It essentially now says, oh, and what's the area under an impulse? If we just integrated, if in this example f of t was 1, then this would be the integral of the impulse from minus infinity to infinity, and we know the impulse has an area underneath it of 1. So now we have really a weighting of 1 that is applied to the waveform f of t, and this weighting is only true at the time instant when this impulse occurs, which in this case is at t equal to 0. So the only thing that this integral of impulse times f of t can do is really push out or produce the value of f of t at time t equals 0. So the integral of this impulse product with f of t is going to be f of 0. What happens when we delay or introduce a delay, or we really shift in time that impulse? Now we remember what's happening. Again, this impulse is only going to be active or non-zero when the argument is 0, and that's when t minus t sub 0 is 0, or when t is equal to t sub 0. That means that this product will only have a non-zero value at time t equal t sub 0. The impulse has an area underneath it of 1, so it's not changing the functional value of f of t. It's simply extracting from this integration process the value of f of t at the instant of time when that impulse occurs, which is at t equal to t0. So now when we have a shifted impulse, it's now going to extract the argument f of t, or I'm sorry, it's going to extract the argument of this integrand f of t, or this function f of t that's in the argument of the integrand at time t equal t0. So now the integral of this impulse that's delayed and occurs at t naught is now going to simply produce as its output the function evaluated at t naught. If we now want to use that understanding to help us try to Laplace transform the impulse, now look at what we have. We could think of e to the minus st as our f of t up above. And what happens? Well, when we have this impulse inside the integrand of an integral, then it's simply going to only be active when the argument of that impulse is 0, or at time t equals 0, and it has the effect of just sifting out this function f of t and evaluating it at the instant when the impulse is active. In this case, the impulse is active at time t equals 0, so this is now going to actually say we need to evaluate this function f of t at time t equals 0, and now we have e to the 0, which is 1, and now we've learned then that the Laplace transform of an impulse will produce, in the frequency domain, a constant value of 1. And this is now called, or the property of this impulse underneath the integral, or inside the integral, is sifting out what you have inside the argument, and it evaluates it when the impulse is alive or active or non-zero, and the only time that's true is when the argument of that impulse is 0, and in this case the argument of that impulse is t, so the only time that impulse is active is at t equals 0. We evaluate the f of t at that time instant, and that now gives us e to the 0, which is equal to 1. And that is the Laplace transform of an impulse.